I'm going to do a quick lecture video on exponential functions. This goes along with the guided notes. So this is the summary page for exponential functions. We can write them in two ways. This is the most common way over here. F of x equals a, some initial amount, times b, a base or factor raised to a power. And so notice here that on this side I have a times 1 plus r raised to a power. So I have my initial amount here, a, raised to a power x, and then I have this term here, 1 plus r and b. So 1 plus r is actually equal to b. The other way I can write it is, if I do a little algebra, r is equal to b minus 1. So sometimes when we're working with exponentials, we're given the growth or decay rate, and then we have to write the equation with the factor b. Sometimes we're given the equation that has the factor, and we want to describe what the growth rate or the decay rate is. So these are all just different versions of writing the exponential function. The initial amount, a, can also be thought of as the y-intercept. When we say initial amount, usually means at, this input equals 0. And if I put in 0 to my function, f of 0 equals a times b raised to the 0 power. But anything raised to the 0 power is equal to 1, meaning f of 0 is equal to a, meaning 0a is our y-intercept. When we have exponential functions, they can either be growth functions or decay functions. And if I look at my rate, if rate is greater than 0 or it's a positive rate, then I have growth. If r is less than 0 or negative, I have decay. Because of the relationship between rate and factor, I can then translate that to, if I'm given an equation looking at my factor, that if b is greater than 1, it's growth, or if b is between 0 and 1, we have decay. And then all exponential functions have horizontal asymptotes, right? In the case of a growth factor, it looks like this. In the case, if I have a decay function or a decay factor, it looks like this. And we always have y equals 0 as our asymptote. That's that horizontal line at y equals 0 of the x-axis. It just depends on what side it's on. So if I have decay, my asymptote is on the right. If I have growth, my asymptote is on the left side. So let's take a look at this problem here. All right. I'm given a function, f of x equals 490 times 0.85 raised to the x. And we can see that it is in this exponential form here, a times b raised to the x. All right, so let's fill in what we have here. So b, I can see, is 0.85. Okay, and r would be b minus 1. So if I have 0.85 minus 1, I get r equals negative 0.15. That's decimal form for r, negative 0.15. If I want to write it as a percentage, I would just move that decimal place over 2 places, and this means that I have a negative 15% decay or decrease. So for every time x increases by 1, my y values decrease by 15% or by a factor of 0.85. I can see that a here is 490, right? We already talked about a being our initial amount, so that's also our intercept, 490. Because I can see that b is less than 1 and r is negative, that means that I have a decreasing function or a decay function. We talked about the domain for exponential functions are negative infinity to positive infinity, and my range is always 0 to infinity. Now, because let's just sketch, I guess, a little bit here. If I know my initial amount is 490, I know it goes through here. Here's the point 0, 490. Okay, and because I know it's a decreasing or a decaying function, I know that it's going to start big and then get smaller like this. So if I want to write my right tail, I'm interested in what happens as my x values get really big. So if I write that in limit notation, it's the limit as x approaches infinity of f of x. So what happens to my y values or my function values as x gets bigger? They get closer to 0. Okay, on my left tail, that's up here on the left side. Okay, so I'm making my x values go toward the smaller end of the domain. So the limit as x gets really small toward negative infinity of f of x, my y values or my f of x values shoot up toward positive infinity. Okay, so we can use Excel to help us evaluate and solve exponential functions. So let me just pull open Excel here and pull this over. So we're going to set up our input-output tables like we've done previously. If I put in, let's start off with like negative 10, and if I go by increments of 2, negative 8, and let's just fill this in a little bit. And this is equal to 490 times 0.85 raised to the x power here. And I really don't actually need this. This is equal 490 times 0.85 raised to the x. There we go. I actually don't need any parentheses around that because of order of operations. And I can see here when I put this in, when I put in x equals 0, I can see that my output y is equal to 490. That's my intercept, which is right over here. Okay, so let's see what it says down here. It says f of 3 is equal to. Well, 3 is my input. It's inside the parentheses. So I can use my input-output table, and I don't have a 3 in here, but I can just type in 3, and it will evaluate it for me. So f of 3 is equal to 300.921. 300.921. We'll fill that in a second. And then if I want to find when f of x is equal to 500, 500 is my output, and I want to solve for x. So I'm going to use solver. So I want to find what number is closest to 500. And actually, it's right here. I'm going to go right here, though, okay? Somewhere between -2 and 0, it's equal to 500, and I'm going to use solver. So I'll do data solver. I want to force this cell to equal 500, the output to equal 500, and I want to put the result right here. And I need to unclick this. Notice that my inputs are negative here. If I don't unclick this box, it's not going to be able to give me an answer because this would make that output value or the result value, force it to be a positive number, which it will not be in this case. So I solve, okay, and I'm going to round this to 4 decimal places. So I can see here that when x equals negative 0.1243, my y equals 499.